Section: Introduction. In this section, we discuss the journey towards creating adaptable robots that can assist with daily tasks. To achieve this, robots must be able to learn new skills as they go along. These skills can range from simple preferences, like knowing which dishwasher a household uses, to completely different ways of cleaning a house. When it comes to familiar skills, humans can easily explain them in natural language. However, for more nuanced or new skills, we often resort to demonstrations. For instance, we might demonstrate how to use a specific microwave or how we like our cabinets organized. For robots to be seamlessly integrated into our lives, they need the ability to generalize from demonstrations, just like humans do. Humans can understand what others intend to do by observing them visually. We often use social reasoning and common sense to grasp the goals of others without them explicitly stating them. This skill is developed from childhood and is used throughout our lives, such as when we watch how-to videos to learn tasks that are hard to explain in pictures or text, like kneading dough or knitting. If robots can also learn to understand the intentions of other agents, it could enhance their interactions with humans and make them more efficient at tasks. This study focuses on visual imitation learning, where robots learn tasks by watching video demonstrations. This method has several advantages. Firstly, it allows robots to learn from different agents without direct control. Secondly, it enables robots to learn from experts who may not be physically present with the robot. Lastly, visual imitation learning is ideal for teaching tasks that are challenging to describe verbally. Current robot manipulation models often rely on text instructions to perform tasks. However, this can be limiting as tasks may have multiple meanings or require different actions based on the context. For example, tasks like open drawer and open jar with screw cap may use the same verb but require different actions. Robots need to be able to adapt their actions based on the specific task at hand. Another common approach is to use a final goal image for tasks. However, this can lead to ambiguity in tasks where the process of performing the action is crucial. Video conditioning can help resolve this ambiguity by providing additional visual context. While language-based policies have shown high success rates, video-based policies have faced challenges due to the complexity of raw video data, variability in task demonstrations, and limited labeled training data. Despite these challenges, learning policies from video demonstrations is crucial for robots. To address the limitations of language prompts, we aim to enable task specification through physical visual demonstrations. Our goal is to develop a system that can quickly adapt to tasks shown in video demonstrations, using end-to-end models with video conditioning. Our work focuses on encoding video task specifications using a transformer-based policy, aligning prompts with robot video representations through contrastive auxiliary losses, and demonstrating the effectiveness of our video conditioned policy through real robot experiments. Section Summary. In this section, we explore the challenges and solutions in enabling robots to learn new tasks through visual imitation learning. We discuss the limitations of language conditioned policies and the advantages of video conditioned policies, highlighting the difficulties in training due to high-dimensional data, variability in task specifications, and limited availability of labeled training data. Our focus is on developing an end-to-end system that leverages video demonstrations for specifying tasks and improving robotic control in real-world scenarios. Section: Approach. In this section, we aim to design a robotic system that can understand a given video of a task and perform the same task in its own environment. To achieve this, we need to train a model that can analyze the video and the robot's current state to predict the actions needed to complete the task. This model is trained using a dataset of paired videos and robot trajectories. To create this dataset, we use three types of data: robot-robot, hindsight human-robot, and co-located human-robot. In robot-robot data, we pair videos of robots performing the same task in different settings. Hindsight human-robot data involves humans mimicking robot trajectories, adding variability to the prompt videos. Co-located human-robot data includes tasks performed by both humans and robots in the same space, offering diverse scenarios. Combining these datasets gives us a large number of robot and human videos covering various tasks. Each dataset has its own advantages and challenges. Robot data is easier to collect but lacks diversity, while hindsight human-robot data adds variability to prompt videos. Co-located human-robot data is the most time-consuming to collect but provides a rich set of diverse tasks. Our model architecture consists of 4 modules: prompt video encoder, robot state encoder, state prompt encoder, and robot action decoder. The prompt video encoder processes the task demonstration video, while the robot state encoder encodes the current robot state. The state prompt encoder combines information from the video and robot state to predict actions. Finally, the robot action decoder predicts the actions needed to complete the task shown in the video. We use cross-attention transformer layers in our architecture to manage the large number of tokens in the videos efficiently. These layers help reduce memory requirements during training and enable effective processing of paired videos. Section Summary. In this section, we aim to design a robotic system that can interpret a given video of a task and generate actions to replicate the task. To achieve this, we train a policy that learns to understand the task from the video and predict relevant actions. We create datasets by pairing prompt videos with robot trajectories, including scenarios where robots imitate each other, humans mimic robot actions, and humans and robots perform tasks together in various environments. Section: Preprocessing. In this section, we handle videos of varying lengths by randomly sampling 16 frames, always including the first and last frames, and arranging them in increasing order of time. During training, we select a robot state by first sampling a random time step. We then choose the preceding 7 frames to create a robot state video consisting of a total of 8 frames before. If there are fewer than 7 frames before the current time step, we duplicate the first frame to maintain a fixed-size robot state video. The pixel values in each frame are normalized between 0 and 1, and each frame is resized to 224 by 224 pixels. Photometric distortions like cropping, brightness adjustments, contrast changes, hue shifts, and saturation modifications are applied during training. The action vector includes values representing the mode, gripper pose and closedness, as well as base displacement and rotation. These values are scaled between 0 and 1 and then discretized into 256 bins each. Altogether, we construct an 11-dimensional action vector where each value ranges from 0 to 255. In our study, we focus on scenarios where the base remains stationary. For training, we use behavior cloning to train Vid2Robot end-to-end. The goal is to learn video representations from raw pixels to recognize task verbs and objects, and to learn motor control to achieve these tasks. We employ a classification loss on actions categorized into 256 bins. The action prediction loss is calculated as the cross-entropy between the predicted action and the expert action based on the robot trajectory and current visual observations. This loss trains all the model parameters. To prevent overfitting and enhance learning features that aid in understanding semantics in prompt videos, we introduce 3 auxiliary losses. The first is the video alignment loss, which aims to align prompt videos with robot videos performing the same task to encourage the image encoder to focus on task-relevant features. The second is the prompt robot video contrastive loss, which applies contrastive loss between prompt tokens produced by robot or prompt videos performing the same task. The third is the video text contrastive loss, which adds a contrastive loss between prompt tokens and those produced by robot videos, along with the text instructions of the task. Overall, we combine these losses for training, which include the classification loss, video alignment loss, prompt robot video contrastive loss, and video text contrastive loss. Section Summary. In this section, we preprocess the video data by sampling frames and creating robot state videos with normalized pixel values and resized frames. We also apply photometric distortions during training and scale action vector values before discretizing them into 256 bins. Additionally, we train our model using behavior cloning to learn video representations from raw pixels for recognizing tasks and performing motor control, while incorporating auxiliary losses to prevent overfitting and encourage learning helpful features for understanding semantics in prompt videos. Section: Implementation. In this section, we trained our model, implemented in JAX, for 200,000 iterations. We utilized the Atom W optimizer with an initial learning rate of 8E5 and a cosine learning rate schedule with warm-up steps of 2000 and a final learning rate of 1E6. Both the prompt and state resamplers consisted of 2 perceiver resampler layers with 64 latents. The state prompt encoder and action decoder each had 4 layers of cross-attention transformers. We conducted experiments involving real robot evaluations for our multitask video condition policy. One of the main focuses was on how well robots can imitate humans performing manipulation tasks, considering differences in speed and style. We examined the impact of using robot and human videos as prompts. Regarding metrics, we defined a rollout as a sequence of actions generated by the policy and executed on the robot based on an initial state observation and prompt video. Success for a rollout was determined by the policy correctly executing the task instruction from the prompt video without needing resets or recovery. We calculated the success rate for each task by averaging the success recorded across multiple rollouts, and the overall success rate was the aggregated success rate across tasks. To evaluate the success of a policy's rollout on a robot, we enlisted human raters. The evaluations involved varying robots, lighting conditions, furniture setups, and objects, with consistent initial object configurations for all policies. Prompt videos unseen during training were used to assess the policy's ability to recognize new tasks. We compared our model with BCZ, a video condition policy using ARESNET18 encoder. Both models were trained on the same data mixture but were tested on new prompt videos. We assessed their ability to infer task specifications from prompt videos and the robot's observed state across 8 categories of manipulation tasks. For each of the 9 tasks evaluated, 4 evaluators conducted 2 rollouts per task, resulting in 8 trials per task to determine the policy's task success rate. The overall success rate was reported for each task over the 8 trials, totaling 72 trials. In total, our evaluations required 288 real robot rollouts. Section Summary. In this section, we implemented our model using JAX and trained it for 200K iterations with specific optimization techniques. We utilized perceiver resampler layers and cross-attention transformers in our architecture for both the prompt and state resamplers. Additionally, we conducted experiments with real robot evaluations to assess the success rates of our multitask video condition policy across various manipulation tasks and prompt video types. Section: What is the gap in success rate due to embodiment difference in prompt videos? In this section, we compared our model with BCZ using robot and human prompt videos. BCZ served as a strong baseline for our comparisons. Our model, Vid2Robot, performed better than BCZ by 20% for human prompt videos and comparably for robot prompt videos. Despite having significantly more training samples for robot trajectories than human videos, there was not a significant performance gap for robot prompt videos. For human prompt videos, our model outperformed BCZ in most tasks, especially in picking from drawers, placing on counters, and opening, closing drawers. We also analyzed how well video condition policies performed when shown a task in an unseen video. Our model reached the correct object 78% of the time, which was 8% higher than the baseline. We observed that grasping errors, especially with small or deformable objects, occurred more frequently in collision-prone areas. Our model outperformed BCZ by 20% in successfully grasping objects. Releasing the object at the correct location after grasping was crucial for success, and both models experienced a slight drop in success rate due to incorrect releases during rollouts. Furthermore, we investigated cross-object motion transfer, where our model demonstrated the ability to perform learned manipulation actions on objects not seen during training. This emergent behavior, termed cross-object motion transfer, was not observed in BCZ. Our model showed better performance, 34%, compared to BCZ, 17%, in transferring motions to different objects as shown in prompt videos. Tasks involving placing objects into drawers showed a significant improvement from 29% to 54% success rate with our model. In tasks like picking from drawers, placing on counters, and knocking over objects, BCZ struggled to perform, while Vid2Robot succeeded 25% to 29% of the time. Section Summary. In this section, we compare our model, Vid2Robot, with BCZ using human and robot prompt videos. Our model outperforms BCZ by 20% in tasks like picking from drawers and placing on counters for human prompt videos, showcasing better task semantics understanding. Additionally, we introduce the concept of cross-object motion transfer, where our model demonstrates the ability to perform learned manipulation actions on objects not seen during training, outperforming BCZ in this scenario by 17%. Section: Ablations. In this section, we presented our analysis of the impact of different loss functions on the overall success rate of our model. We explored two scenarios, one without any auxiliary loss and another with an auxiliary language loss. We conducted evaluations on 9 tasks for each policy variant using 3 model versions: the original Vid2Robot, one without video text contrastive loss, CL, and one with only action prediction loss. We had 3 human evaluators run each model variant with 2 rollouts each, totaling 162 rollouts. The results, shown in the figure, indicate that not using any auxiliary loss significantly hinders our model's performance, with a success rate of 45% compared to 61% when incorporating auxiliary losses. This underscores the importance of the proposed auxiliary losses. When examining the impact of the auxiliary language loss, we found only a slight 1 to 2% improvement in success rate. This suggests that video alignment and contrastive loss play a more significant role in enhancing performance. Our findings suggest that effective video representations can be achieved without relying on auxiliary losses using pre-trained language embeddings. Our study contributes to the understanding of how auxiliary losses influence the success of our model. We aim to demonstrate that leveraging video representations for policy conditioning is crucial for enhancing robot learning capabilities.